Our next speaker is Dr. Stephen Lee, hails from Ohio State, and Dr. Lee is on the Faculty of Biomedical Engineering at Ohio State University. He has published extensively in the field of engineering receptors of field effect protein sensors for maximum sensitivity and immune mitigation of recombinant proteins and protein nanomaterial biocompatibility. Following on a comment that Dr. Blumberg just made, there are structures of all different sizes in the bloodstream. Proteins are often some of the larger ones, and it would be really filling in a lot of the gaps of what was talked about this morning to hear your talk, Dr. Lee, on nanorobotic protein interaction. So I've been really looking forward to it. Welcome to the podium.
So I'd like to thank the organizers for inviting me to this meeting. This is a very fun group. This is a group of people you can go and interact with and come back refreshed. And that's a real pleasure, so thank you very much.
You're most welcome. Thank you.
And so I'm going to be talking to you about things that, compared to some of the stuff that we've seen, is relatively unsophisticated. It's operating on a simple first principle level. And to explain why I'm going to be talking to you about it, I'd like to give you a little background about my history and how I got into this particular problem. And so my training is as a bacterial geneticist, and my primary expertise was in the engineering and heterologous expression of foreign proteins. And one of the things that one notices when one looks at the biological world is, in contrast to what's been done in the pharmaceutical world, you're not just simply a bag of enzymes, but the pharmaceutical world has chosen to make relatively few soluble proteins that are easily druggable. Now, this has changed substantially since the time that I originally was thinking this and having my dissatisfaction with being a pharmaceutical biotechnologist. But the bottom line is that as a biologist, I was well aware that, in fact, higher order organization really caused a lot of the sophisticated biological functions that we see in living things to emerge. And I was seeing it in the biotech industry. There was really fairly limited interest in exploiting that. And it occurred to me that nanotechnology might offer an opportunity to use protein materials in such a way that you could use the nanoparticles and the materials to aggregate and organize the proteins, get them to perform complicated tricks that they would not perform as freestanding admixtures of the protein components. And so what I'm going to talk to you today is something that's on the very simplest level of that argument. And what I'm going to talk about is engineering of polypeptides for particular function in nanomaterials or in nanodevices. And some of you would probably feel that the argument that I'm going to place has already been made and successfully answered. What I really wanted to be able to do was to identify a problem where there was a specific problem at nanoscale that could be addressed by a directed specific engineering activity in a protein constituent of a nanodevice. And so let's see, how do I cue the first slide here? Press this. Very good. Okay, so what I'm going to talk to you about is something that's really fairly simple, very straightforward. The devices themselves are actually microscale, but the problem actually occurs at the nanoscale. What I'm going to talk about is a class of devices that were largely discredited in 1991 by an article by Pete Bergveld. And basically what I'm talking about is FET sensing of polypeptides. And so FETs are field effect transistors, and let's see, is this, am I getting, how do I get very good. Okay, so FETs are field effect transistors. They consist of a semiconductor device, source, a drain, a capacitance layer, and then to get these devices to sense proteins, what you do is you put some sort of a specific receptor onto their surface, and the specific receptor recognizes a particular protein analyte. The analyte binds. The proteins themselves have some intrinsic charge at any given pH, and so you induce a field effect, either positive or negative, and we work with N-type devices. So if it's a positively charged protein, you increase the current through the device. If it's a negatively charged protein, you shut it down. And this method of sensing was largely discredited for function in physiological salt conditions about 20 years back. And this is an erroneous model that was published supporting discrediting this model. And I won't go into the details of what's wrong with this, but suffice it to say it represents a misunderstanding of antibody and protein structure. And the argument was that basically antibodies and immunofets would bind to the surface of fets and recess the analyte so far away from the surface that a shielding layer of ions would form at physiological salt concentration, and effectively you would be unable to see your, boy, I seem to be losing my pointer. You would be unable to sense the bound analyte. And as it turns out, that's not true. And so we published this a couple of years ago. We use HFETs, and so they're a heterojunction structure. We've heard a little bit earlier today about heterojunction structures in some of the motive nano devices, but basically the electrical conductivity of the HFET comes from a crystal lattice mismatch between the layers of the heterojunction device. And so what we did was that we took an HFET and we deployed a SAM onto the surface, put an affinity element onto the surface, and we could bind either a positively charged analyte, monokine induced by interferon gamma, or bind a negatively charged analyte, strepavidin, and we produce a predictably, a sensing result that is predictable in its direction and magnitude. And so to make a FET sensor that's useful for detection of MIG, which is a protein that is associated with high levels of inflammation, what we would have to do from that original device that we published a couple of years ago is to push down the sensitivity limit a couple hundredfold. Okay, and so what I'm going to talk about then are protein engineering approaches that allow you to do that. So in the case of the HFET, so as I mentioned, Bergveld discredited the idea of FET sensing at physiological salt concentration. But what we see in our devices, we really are sensing the proteins, because just as the model predicts, in fact, sensitivity is inversely related to salt concentration. And so the signal that we generate is higher in lower salt buffers than it is in higher salt buffers. And you can do a whole series of dilutions of the buffer, and the sensing signal goes up as you increase the dilution of the buffer. So from the standpoint of the model, they're correct that shielding occurs. They're not correct that you can't sense at physiological salt concentrations. So let me show you. Basically what we're going to do is that we're going to take our FET sensing device, and here are some of the opportunities for optimization. And so what I'm going to talk to you mostly about are the things that are in red. Specifically, I'm going to talk to you about optimizing the receptor for the FET, in terms of its size, its topology, its epitope specificity. I'll talk to you a little bit about the particular characteristics of our analyte that make it highly amenable to FET sensing, and if we have time, I'll talk a bit about optimizing the polymer film that's used to link the specific affinity element to the FET sensing surface. Okay. So we're working, you've heard me mention the analyte, which is called MIG, monokine induced by interferon gamma. It is a protein that is evolved rapidly, very early on in inflammatory processes. And so MIG is a protein whose concentration is directly related to the inflammatory state of the tissue. And so this sensor is initially intended to be used as a device that will allow you to monitor the inflammatory state of a transplant and be able to see incipient rejection events which are occurring. So that's the proximal reason for doing this. And so MIG has a concentration that varies between about 40 picomolar in a non-inflamed tissue up to about 34 nanomolar. It's very, very attractive for FET sensing approaches because it's highly charged. It has a net charge at pH 7.4 of about 20 positive charges per molecule. So binding MIG brings in a lot of charge. It's very suited to a FET sensing modality. So, in the original model, the assumption was that you would use intact antibody fragments. And this is a diagram of an antibody, and there is no reason to do so. You can see the antibody itself consists of variable regions, shown here in red, and then constant regions, shown here in blue, which have effector functions. Only the variable regions are actually involved in contact with foreign epitopes and antigens. And only the variable regions are necessary for specific recognition of a foreign protein. And therefore, in the initial model, the assumption was made that this 12 nanometer tall structure was necessary. In fact, it's not. Since the model was initially published, people have learned how to make single chain FVs, and these things are about 3 to 4 nanometers in height. Here we have the variable heavy, the variable light, and here we have the CDRs that contact the antigens on the surface of the single chain FV. And so, in fact, you can substantially reduce the distance between the bound analyte and the sensing surface simply by moving away from these full-length antibody fragments down to an engineered single-chain FV. And so the way that we get the single-chain FV, many of you no doubt are very familiar with it, is that we use a high-throughput display method. And so basically this is a diagram of filamentous bacteriophage in which you have your favorite protein presented as a fusion to one of the phage proteins and encoded by the DNA encapsulated in the virus. And this allows you a very convenient means to select out of a library of variants those proteins which recognize the protein of interest. And so basically the procedure is that you construct a library that has 10 to the 9 to 10 to the 10 individuals, and you take this pooled library, you expose it to your analyte of interest, in our case to MIG, you incubate it, you allow it to bind, you isolate the MIG-bound phage particles, wash away the rest, and then you elute the phage and repeat the process. And what you end up with is that the phage enriched. A larger and larger fraction of the population as the selection goes on is capable of recognizing MIG. So this is just standard phage display technology. Okay? And so for the purposes of engineering this protein for its use in the sensor, there are a couple of things that we want to do. So we wish to be able to use chemoselective conjugation. We want to be able to orient the protein on the sensor surface. And so what we use is an oxyamine conjugation chemistry. All chemoselective conjugation chemistries consist of a nucleophile electrophile pair that are mutually exclusively reactive for one another. And so what one can do is if you have two chemical constituents that contain such a nucleophile electrophile pair, and typically the electrophile is an aldehyde or it's some sort of an alkane group. And then if you have a nucleophile, in this case an amino-oxy group, you will form a specific oxime bond only at this site. And one of the things that we discovered early on when we were playing with these proteins is that if you put an N-terminal serine at the beginning of a polypeptide sequence, and then you expose that polypeptide to mild oxidation, the serine is converted to an aldehyde, which provides you now with an electrophile. And so if we derivatize the surface with the SAM that contains a nucleophile, it now becomes possible to do oriented deposition of your antibody fragments. And so basically what we're showing here is the molecular biology just simply to reduce or to replace the N-terminal alanine of one of the single chain antibody fragments with the serine, and then subsequently oxidation and expression, and you are able to then generate a protein which will participate in the chemoselective conjugation. And this is mass spec data that shows that in fact the chemoselective conjugation is very specific. So for the individual proteins, what we show here is with the sear-terminated proteins, there is a single residue that undergoes a predicted size mass shift when one does a light oxidation of the protein. So here we have the unoxidized form, and here we have the oxidized form. And basically, we get a mass shift of the expected molecular weight. It's about 16 atomic mass units. And that indicates that when we oxidize the protein, we are only changing a single residue, and you can delimit where that residue is by trypsin digesting the polypeptide, and then running the mass spec again and asking in which fragment the mass shift occurs, and it occurs in the N-terminal fragment. So in fact, what you're doing is producing a aldehyde that occurs only at the N-terminus of the polypeptide, and what that means now is that I'm capable of doing chemoselective conjugation of this single chain Fe onto the surface. And so there are a couple of things that you could do that would reduce the critical distance between bound analyte and sensing surface to enhance the sensing signal. And a couple of them are very simple. One is that when you do these phage display methods, what you always get is a selection of different ligands that recognize whatever your target protein is. And so, in other words, in the case of the single chain Fes, these are things that recognize different MIG epitopes. And so, in principle, the consequence of having receptors that recognize different epitopes is shown here. So if you hypothetically say on MIG that you've got 2 epitopes, which is untrue, there are probably 8 or 9 groups of epitopes in a protein this size that are not overlapping. But basically this shows an assay that would allow you to determine that in fact you have more than one antibody specificity for epitope. But the interesting thing about it is obviously the charges on MIGs are fixed in space, and the epitope positions are fixed in space. So if I use as a receptor an epitope or a antibody that recognizes a particular epitope, and compare that to another antibody that recognizes a different MIG epitope, one would expect that the charges on the surface of MIG would be moved relative to the sensing surface. So this is one way in which one can tune the sensitivity of the device, but you can only take advantage of this if you have access to chemoselective conjugation. Okay, another way in which you can take advantage of, I'm going to fill this in a little bit. This is a model of MIG, and what this shows is the white residues, it's a space-filling model, are uncharged amino acid. So the blue residues are positively charged, the red residues are negatively charged. And so if you allow, if this is my single chain Fe, and it's down on a surface, if you allow this to be the single chain Fe, depending upon which epitope my antibody recognizes, I would expect that it would bind MIG either in this sort of configuration or possibly in this sort of configuration or possibly in this sort of configuration. But what you can see is that I'm moving around the position of the charges relative to, this sensing surface, right? So I can adjust proximity this way. Another way in which one can adjust proximity, which surprised the living daylights out of it when we first did it, is that polypeptides in particular are extremely amenable to circular permutation. So what is circular permutation? Well, think of the linear amino acid sequence. Imagine that you join that into a circle, right? So you seal the N and C ends, and then you create another N and C end somewhere else on the surface. So you're moving around the domains of the protein relative to each other. And what we found when we did this as a phage display exercise, we initially did it with a 4 helical bundle protein, and it was GCSF. But what we found was, remarkably, out of the library of variants, about a half of the circularly permuted forms of the GCSF molecule were fully capable of engaging receptor. So they were functional, and this was a surprise. This is a rather gross perturbation of the protein sequence, and yet we retain function. You can do the same thing with antibodies, and the consequences are shown here. And so here we have our single chain FV. This is the variable heavy, variable light. These are the CDRs in pink. And what you can see is I've used chemoselective conjugation that hits only at the N end of the polypeptide. And just as is the case with the circularly permuted 4 helical bundle protein, if I use chemoselective conjugation and I circularly permute the proteins, the relative position of the various domains of the proteins relative to the sensing surface is changed, right? So in actual fact, I can tune proximity of these antigen binding domains of the single chain FB by permuting the molecule. Okay, so there is another mechanism by which you can use some protein engineering to specifically adjust distances, nanoscale distances within this device. Now, I won't cover this, but suffice it to say there's an opportunity also, if you have a SAM on the surface, to shorten up the SAM to make the SAM more ideal, and that also affects sensitivity. So I will skip over these points. These have to do with my ire with the existing conventional wisdom about the infeasibility of FET sensing at physiological salt, which isn't true, but I had a horrible time funding this work when I first did it. I basically had to do it first and then show that it worked before I could get funding, and that's extremely frustrating. But what I will tell you is that I think that the experiences that, that we've had here indicate that, in fact, you can tune the proteins for very specific function to address a nanoscale problem. In this case, the nanoscale problem is the critical distance between charges on analyte and the sensing surface. And I've shown you a couple of mechanisms by which you can adjust it. And so what that says to me is that hopefully within nanotechnology, there may be a role for persons like myself to play. And so I'm hoping that we molecular biologists actually can play a role with you guys. And so I took on this project as a way to demonstrate that we could address such a problem. And the folks involved in generating this were my graduate students, my collaborators in the Department of Electrical Engineering who made the Algan heterojunction structures, Wu Lu, Len Brilson, Suzhen Wen. And then we didn't cover this, but I also have collaborators in the OSU Department of Material Science who helped me characterize the SAM on the surface and the protein-SAM interfaces for thickness, robustness, and a number of other parameters. And of course, one always has to acknowledge who gives you the money to play with. And so in our case, it's National Science Foundation and Department of Homeland Security. So that's it. Thank you for your attention, and I'll take any questions you might have. Yes, sir.
Hi, I'm Tad Hogue.
Yes, yes.
So do you have kind of anything you can say about false positives and things? Are there other sorts of proteins around that might bind more weakly but have higher concentrations?
So that depends so there's two factors that determine whether or not that's a problem for you. One is, as you're well aware, MIG is a chemokine. It's part of a large family of related proteins. And so like I was emphasizing how important it is to select the correct epitope recognition specificity to get maximal sensitivity. It's also important because some of the epitopes are conserved from chemokine to chemokine, right? And so you can end up reading other proteins. Okay, but what we can say and what others who have been working with FET sensors can also say is that there is a specific fingerprint, if you will, electrically of the polypeptides because, you know, so two chemokines, even though they share an epitope in common, overall have different amino acid sequences. And you can pick apart which chemokine had to be on your sensor by shifting the pH and watching the response of the sensor as a function of the shifts in the pH. Yes, sir. Oh, it's surface chemist.
Jay Hickman, UCF. I think what your research is doing, simulation and modeling are great tools, but I think you've shown is that the pratfalls of over-interpreting it sometimes and ruling out whole areas of interest. But very, very nice chemistry, surface chemistry that you've done.
Thank you.
Did you actually do any of the measurements in serum or just even in
so
BSA solutions or anything else like that?
So mostly we've done them in a physiological buffer because so basically in PBS, but we're starting now to do them in serum. And the question I bet you're ready to ask is, am I getting other gunk onto our sensor?
Well, no, of course you are. But so the question is whether or not.
Well, thank you.
No, you are. Just
yeah,
50 years worth
it's unavoidable.
Yes.
Yes.
But the point is, what I'm curious about is whether or not the other proteins and everything are going to disrupt the very nice and elegant surface chemistry you've done, because sometimes they do hold up. That kind of chemistry does hold up in physiological situations. It'd be interesting to see whether or not yours does as well.
So I can't tell you for certain at this point. I'm expecting that, so there's a lot known about the oxime conjugation chemistry, and the oxime bond is, unlike some of the other chemoselective conjugation, is not very labile. So I expect it will.
I'm not worried about that aspect of it because, I mean, Carolyn Bertozzi has shown that you can actually decorate the outsides of cells with it and do chemistry in physiological systems. So that's fine. It's whether or not you can actually retain the orientation on the surface.
So one of the things I glossed over and what you're sort of alluding to is that these things have some conformational freedom, right? They're not rigid bodies.
Right.
Okay, and so by and large, so I have oriented them to some extent, but I expect that there are a variety of different possible conformations that this system adopts.
Well, because what's really interesting is when the other proteins absorb and in some cases denature, you get this reorganization effect. And I'm wondering whether that reorganization is going to involve your molecules or not, or whether or not you've got it stable enough.
So I can't
because
tell
that'd be
you.
very interesting to find out, because then you would have something that would hold up under physiological conditions.
So that's a significant issue. I can't tell you what the answer is right now.
Got a question from Dr. Borges is next, right behind you. Oh, yeah, there.
Yes, sir.
Allow me. A little difference in height.
That was
Bob
interesting.
Borges from UAB. I just wanted to comment. I admire your persistence. You knew.
Thank you.
You knew you were right. You were right, and you proved it. Great job.
Thank you. Thank you.
Okay, sorry, sir.
Again, it's really beautiful presentation. And I wonder about masking effect. Since you're dealing with charged molecules, you're always worried. I mean, you show a very nice problematic effect of the ions, but you have a lot of, I'm not sure you aim really to get the effect in the serum at all. You may look for a local effect that may be a little bit cleaner, isn't it? Or what you're looking for?
Yeah, so in actual fact, I don't know how the sensor performs in serum. That's one of the things we intend to do next. But yeah, what you're suggesting is a potentially significant problem. I just don't know the answer yet.
Yes, please.
Yeah.
Yeah, so this was beautiful, and this is, I guess, more of a comment than a question. It was, I thought it was a little modest about the possibilities of using this sensor, because this interface, this antibody-antigen interface, is actually something that has undergone at least 400 million years of research and development before you started on it. It is designed to operate in the environment where you're operating it, in serum. And it seems like it has a tremendous potential for high specificity interactions under the conditions where you're looking for them.
I hope so. I can't say with certainty because I haven't done the sensing experiments in serum, but I hope so. Remember, these are also, the libraries I'm using are semi-synthetic. These are actually antibody fragments that to some extent are not precedented in your natural repertoire. So there may be some differences, right? So the CDRs are actually made by synthetic oligochemistry.
The CDRs are made that way, but the frameworks are natural.
Yes, absolutely correct.
And that's the way the immune system works, is that everything in your repertoire is, well, not everything in your repertoire is to some degree new and never tested before.
Yeah, so your repertoire.
I mean, I don't want to get in a big argument over this, but it's a nice system.
Yeah, your repertoire probably contains something like 10 to the 10 to 10 to the 11 different specificities, right?
More.
Well, B cell repertoire is what I was.
Potentially much more.
Okay, well, okay, very good. Well then, all right, I'll take greater credit. Thank you for that. Thank you very much.
Well, thank you very much for honoring us with that trailblazing new research, which I agree is going to open up many promising therapeutic avenues in the years to come. That's exactly the kind of presentation that this conference revolves around, so thank you. Bringing together the biological with the physical engineering. We are now approaching the lunch hour. I want to give you a couple of logistical heads-ups. One of our keynote speakers, Ray Kurzweil, has just texted in that he's grounded. His plane is grounded due to the snow. Not completely surprising, given that even Interstate 10 is closed, which in Canada is really saying something. So what we're going to do is move up the start of session 3 to 1 p.m. and then we'll just break, the afternoon session will just break 2 hours earlier than otherwise. So if any of you have an itch to ski, you probably have a chance to get a few runs in across the street here. So we'll start promptly at 1 o'clock with the 4 speakers of session 3. So please be prepared then. And until then, everyone is welcome to join the lunch downstairs.